The laws of physics are a lie, and the universe is changing. The laws of physics are rewriting themselves, and they've been hiding it from you. In 2025, the cleanest data we have says the rules are shifting under our feet. And if that's true, your clocks, your GPS, even what same means start to bend. Here's the 10-second hit. The laws of physics have patch notes, and the update already shipped. If that lands, universal goes local, and everything you time, triangulate, or trust starts to tilt. The spectrum shouldn't do this. The iron line splits wrong by a few parts per million, like the universe breathed differently when that light left. In a dark room in Chile, someone whispers, "Check the calibration." They do. It still tilts. Screenshot this. They didn't tell you the laws have patch notes. If this holdout is real, the laws aren't fixed, they're moving. And if they're moving, your clocks, your GPS, your idea of same across time all bend with them. We go back to the constants we teach as fixed, C, H-stroke charge, and the buried anomalies that refuse to die. If the rules are shifting, every prediction wobbles. The laws are changing. The first crack, the fine structure constant whispers. Reality isn't fixed. Your ruler is lying and your clock is in on it. Here's the stake in the ground. If the fine structure constant, alpha, drifts, electromagnetism itself changes. Screenshot this. Alpha isn't a number, it's a treaty. If it moves, the universe renegotiates everything. Screenshot this line. Alpha is not a suggestion. It's the handshake every electron makes with light, and the handshake looks different across the sky. Alpha isn't a unit choice, it's a pure ratio. How fiercely electrons feel the pull of electric charge balanced against the quantum tick of light. Chemistry, spectra, stars, all of it leans on alpha. Move it by a whisper and the entire score shifts. Nobody talks about this outside the footnotes, because if it's true, everything we teach about reality is incomplete. The implication is ugly. Universal constants might be coordinates, not commandments. Screenshot this. If it isn't dimensionless, it's decoration. Change a pure number, you change the world. So the hunt went to the farthest lighthouses. We have quasars. Their light crosses billions of years, threading through cold clouds of gas. Those clouds stamp fingerprints, absorption lines onto the beam. Compare the spacing of different lines from different atoms and ions and you get a test. Was alpha the same out there then as it is here now? Teams built a method with a blunt name and sharp teeth, the many multiplet method. Instead of banking on one transition, they compare a web of them, each with a different sensitivity to alpha. If alpha changes, the web distorts in a telltale pattern. If it doesn't, the pattern stays flat. Early on, the Keck telescope in Hawaii hinted at something odd. Looking back in time, some absorbers seemed to prefer a slightly smaller alpha. Not wildly different parts per million, but the pattern held across dozens of systems. It wasn't a proof, it was a whisper. And whispers, if you're careful, are worth following, especially when nobody wants to rewrite the textbooks that say constants don't move. Meanwhile, across the world in Chile, the Very Large Telescope was gathering its own trove of spectra with UVES, the ultraviolet and visual HL spectrograph. Different hemisphere, different instrument, different calibration pipeline. Independently, the VLT sample suggested the opposite trend, alpha a hair larger in the distant gas. That could have buried the whole idea, two big datasets pointing in different directions. Here's where it gets interesting. Put the two together and a picture emerged that wasn't just up or down. It looked like a dipole, a gradient across the sky. In one broad direction, alpha trends smaller with distance. Spin around and it trends larger. The amplitude, still only a few parts per million but statistically stubborn, about 4, 1 sigma in some combined fits. Not ironclad but not easily shrugged off. Stakes again. If that dipole is real, it says space itself carries a preference, like a faint cosmic breeze nudging the laws. That breaks the comfort of isotropy, the idea that on large scales every direction is the same. It doesn't trash physics, it complicates it. Constants become fields, values become coordinates, and our models need to allow for a tilt. This is the slide you won't see in a general audience talk, because it sounds like heresy, a preferred direction touching the rules themselves. Screenshot this. If the sky has a preferred axis, your definition of universal just got local. But data don't confess easily. The pushback came fast and fair. What about wavelength calibration? HL spectrographs rely on reference lamps and cross-orders. Tiny distortions, long-range wavelength stretches, intra-order wiggles could fake a drift. Different spectrographs have different fingerprints. Even the way light fills a slit can bias measurements. Rival teams re-reduce the same raw exposures, stitch together refined calibration procedures, and tighten the error bars. Some claim the dipole fades when you correct long-range distortions. Others found the signal persists, shifting but not vanishing. Environmental systematics inside the telescopes, temperature, pressure, flexure made the list. So did isotopic abundances in the absorbing clouds. If magnesium or iron isotopes in the early universe weren't in the same ratios we assume, the lines shift. That's a real astrophysical wrinkle, not just an instrumental one. Behind every plot there were people. Postdocs who could have played it safe, but chose to publish deviations so small you can't see them without 1,000 careful steps. Senior scientists who spent nights rerunning pipelines, chasing down stubborn half-pixel ghosts. Conferences where the first slide says, "This could be systematics," and the last says, "But we don't have one that explains it all." Careers staked on a claim that might evaporate with the next calibration lamp. And yes, the quiet resistance. Reviewers who write extraordinary claims require extraordinary evidence, while moving the goalposts one calibration at a time. Here's a human moment. A researcher stares at residuals that won't flatten. They email a rival, the kind who critiques every comma. The reply lands at 2:13 a.m., 2 suggestions and a warning. You're either seeing the universe or you're seeing us. That line stuck. Parallel tracks kept running. Laboratory measurements of alpha got sharper. Electron G2, quantum Hall recoil experiments, pinning the local value to absurd precision. That framed the cosmic tests. If there's drift, it's small. And yet the quasar spectra, when binned by direction, kept tilting. The more data, the more the map of the sky seemed to prefer an axis. What nobody knew at the time was whether this was a lone anomaly or the first sign of a broader pattern. Other dimensionless constants murmuring the same tune. If alpha shifts, maybe the proton-electron mass ratio wiggles too. If fields control these values, gravity might couple to them, inviting fifth forces. Suddenly, a few ppm in distant clouds are knocking on doors we keep locked. Callbacks tighten the stakes. Clocks say drift is less or equal to 1018 per year here. Oklo's 2 billion year ledger agrees. Yet deep sky spectra still whisper. Immediate impact. The community tightened standards. New calibration strategies using laser frequency combs started replacing old lamps, flattening wavelength errors by design. Next-generation spectrographs promised fewer excuses. Meanwhile, the older datasets were recut again and again, each pass removing one more conceivable bias, like sanding a table to find the wood grain under the varnish. This was the moment everything changed for the story, if not yet for physics. The idea of a spatial pattern made the debate less about, is alpha smaller or larger in the past, and more about, is the universe slightly anisotropic in a way that touches its constants? It gave theorists a target. Build a mechanism that can paint a dipole across cosmological scales without wrecking everything else we measure. While that was happening in Chile and Hawaii, another witness waited in the most precise labs on Earth. If alpha drifts, even by a hair, time itself, measured by our best clocks, should start to disagree. If laws are weather, clocks become storm gauges. Field hint lab verdict. We leave starlight and ask clocks if the rules are moving now. Atomic clocks start talking, timekeeping versus time itself. Time isn't what you think. Atomic time is a peace treaty, not a law. Screenshot this. If the laws drift, atomic time is just a consensus fiction that needs a weekly patch. If alpha drifts, the universe won't announce it with fireworks. Our best clocks will just start to disagree. That's the stake, timekeeping versus time itself. Navigation satellites, finance timestamps, power grid phasing, everything assumes the ticks are identical everywhere. If the constants move, the ticks won't line up, and the world we've built on synchronized pulses starts to slip. Nobody tells you this when they sell atomic time. It's only as absolute as the constants behind it. Action starts in quiet rooms filled with lasers. Optical lattice clocks trap thousands of atoms, strontium, ytterbium, floating in a standing wave of light tuned to a magic frequency where two atomic states shift together. That trick neutralizes one of the nastier systematics and lets you stare at a narrow transition that barely blinks under perturbation. Meanwhile, single-ion clocks, aluminum, ytterbium ions, bet on one perfect atom, shielded, interrogated, counted. Different species respond differently to alpha. That's the whole point. Teams compare frequency ratios, not just absolute frequencies, because ratios cancel noise. If alpha changes, those ratios drift with telltale slopes. This isn't one experiment, it's a global relay race. NIST tightens one link, NPL another, PTB and RIKEN polish the rest. Fiber links snake between labs. Frequency combs slice optical light into countable teeth, bridging colors to microwaves to compare everything with everything. Year after year, the plots extend. The slopes, usually indistinguishable from zero with uncertainty bars shrinking like a vise. Constraints tight, parts in 1017 then approaching 1018 per year with state-of-the-art optical clocks now bounding drift at roughly 1018 per year locally. But every so often, a trend flirts with significance. A tiny slope over a few years, a wobble that tracks Earth's orbit around the sun, hinting at a coupling to gravitational potential, not time. Then the next data release flattens it. Systematic, maybe, temptation, always. Complication lives in the margins. Temperature shifts in the lab floor feed into blackbody radiation shifts. Laser intensity breathes, changing AC stark shifts. Collisions between atoms in the lattice nudge the transition. Magnetic fields creep. The teams fight each gremlin with metrology jiu-jitsu. Cryogenic environments to quiet blackbody noise. Quantum logic readout for ions that don't fluoresce. Interleaved operating points to subtract biases. Remote comparisons over stabilized fiber to avoid transporting clocks physically. They don't just run one clock, they orchestrate a network. QSNET and similar consortia set a goal, cross-compare dissimilar clocks for years. Strontium versus ytterbium lattice, aluminum versus ytterbium ion. Add in molecular systems, calcium monofluoride molecular ions, whose vibrational lines lean hard on the proton-electron mass ratio mu. If alpha drifts, one set of ratios moves. If mu drifts, a different pattern moves. Overlapping sensitivities turn the network into a fingerprint scanner for physics. Here's a human moment. A grad student watches an overnight run, every data point a tiny dot marching across a screen. The lab hums, the air smells faintly of warm electronics. 2 a.m. coffee cold, a text from a collaborator on the other side of the world. Check the room temp log. The HVAC hiccuped by half a degree at midnight. The slope you thought you saw dissolves when you correct for it. Relief and disappointment land together, hands on temples, a long exhale. Back to zero, back to truth. And in the group Slack, a pinned message, no press, not yet. Impact arrives in two directions. First, the limits themselves reshape theory. If alpha is dancing, it's doing a slow waltz, not a sprint, constrained to change less than a part in 1018 per year locally. That squeezes models where a rolling scalar field pulls constants along. If a field drives the quasar dipole, it either barely touches Earth today, or it couples in ways that hide from these clocks. Second, the very act of pushing precision remakes timekeeping. Optical clocks now outrun the old cesium definition of the second. The metrology world is preparing to redefine time on optical standards, locking civilization tighter to the quantum bones of matter. But there's a subtle twist the lab folks lean into: gravitational redshift. Move an optical clock up or down a few centimeters and you can measure Earth's gravity. That's not a side project. It's a new tool called chronometric geodesy. Build a continental mesh of optical clocks and you map gravitational potential in real time. The same mesh, watched for years, becomes a drift detector. If a cosmological field is whispering through physics, a spatial pattern should imprint on the network. That turns the planet into a physics sensor, and your city into a pixel on a live map of reality's drift. Meanwhile, speculative hints keep popping up. A few studies report annual modulations in ratios, matching Earth's distance from the Sun. Others put strict upper limits on any coupling between fundamental constants and gravitational potential. The battle is in the decimals. Every time a group claims a wobble, 3 others try to crush it with better control, longer runs, different atoms. Today's best limits push drift down to roughly 1018 per year, and null out most proposed seasonal couplings. What nobody knew 5 years ago and people are quietly betting on now is whether clocks will make the first definitive catch. There's a nuclear clock on the horizon using thorium-229's ultra-low energy nuclear transition. If that transition is as sensitive to alpha and the strong force as predicted, it could be the new champion, less noisy, more responsive to the physics in question. If constants drift, a thorium clock might see it first. Thumbnail line: the second is about to change. Stakes again. If these clocks stay flat for another decade, many varying constant models will be on life support. If a cross-checked, multi-species network sees a coherent drift, everything from quasar data to quintessence gets a hard shove. Either way, the lab has become a courtroom where the universe testifies under oath. While that quiet trial continues, the Earth already ran a long experiment for us. 2 billion years without a lab notebook, but with results etched in ore. The natural reactor that shouldn't exist, Oklo's fossil physics experiment. The Earth left us a warning. A reactor ran for 300,000 years without us and kept the receipt. The Earth left us a lab note in stone. 2 billion years ago in what's now Gabon, a uranium deposit did something nobody expected. It went critical on its own. No control rods, no concrete dome, just groundwater trickling through rich veins of ore, moderating neutrons until fission lit. It pulsed for hundreds of thousands of years, heating, boiling off water, pausing, then starting again like a breathing geologic heart. When it finally died, it sealed a message in isotopes, a record of physics as it was back then. Here, that's why that matters to alpha, to constants, to our whole argument. Fission isn't just heat, it's a ledger. Each neutron capture and decay leaves behind ratios: samarium, neodymium, ruthenium, xenon, shaped by nuclear cross-sections. One of those is especially sensitive to the fine structure constant, samarium-149. Its ability to eat neutrons spikes near a resonance whose energy depends on the strength of electromagnetism threaded through the nucleus. Shift alpha a hair, and that resonance slides, changing how many neutrons samarium-149 grabs, and therefore how much samarium-149 survives in the rock. In the early 1970s, French chemists noticed that the natural uranium shipped from Gabon had less uranium-235 than expected. That's the fissile stuff. It looked like someone had already used it. The investigation led to Oklo and then to a forensic read of the reactor zones. 72 tons of uranium-235 gone, traces of fission products right where they should be. It wasn't a fraud. It was a fossil reactor. Now take that fossil and turn it into a test. Measure the samarium isotopes. Reconstruct the neutron spectrum that must have existed to fit those ratios. Ask what resonance energy for samarium-149 would produce that spectrum. Then translate that energy into a bound on alpha at the time. Do the same with other isotope pairs to cross-check. Neodymium's tell, xenon's trapped gases in ancient minerals. Each one points, indirectly but consistently, to the nuclear environment and the constants that set it. Nobody told the rock to lie for us. It still says little or no drift here. The headline result: repeated with refinements for decades. If alpha changed at all since Oklo ran, it didn't change by much. The bounds land at parts per 10^8 over 2 billion years. In plain terms, less than a few parts per 100 million. That's a wall for any theory that wants alpha to be wandering fast. Oklo says, not here, not by much, not in the deep past of this planet. But here's the twist scientists argue about in hotel lobbies at conferences. Interpreting Oklo isn't plug-and-play. The neutron spectrum depended on the reactor's geometry, the water content, the temperature cycling, and the composition of the surrounding rock. The resonance energy in samarium-149 doesn't depend only on alpha. It leans on the strong force too, on nuclear structure encoded in models that carry their own uncertainties. The translation from "we measured samarium" to alpha was X plus or minus Y passes through a forest of nuclear theory. So the debate lives in the error bars. Update the nuclear models, rerun the Monte Carlo simulations of how the reactor breathed, and you can nudge the inferred resonance by a few tens of millielectron volts. That's enough to shift the bound on alpha's change by a factor of a few. It doesn't open the floodgates. It does keep the door cracked for slow drifts and for compensating changes, alpha moving one way, a strong interaction parameter sliding the other, leaving the resonance almost put. Human angle. Imagine being the person who spends 3 years coaxing xenon atoms out of ancient mineral inclusions, molecule by molecule, to count isotopes from a reactor that shut off before complex life walked. Or the geologist who maps the reactor zones, hands black with laterite, trying to reconstruct where the water flowed. Or the nuclear theorist who stares at a line in a calculation and realizes a correction term everyone ignored in 1985 might matter at the exact sensitivity Oklo demands. Every small fix warps the story slightly. The humility is baked in. This is a time capsule, but not a perfect one. There's also a broader meaning that makes Oklo more than a bound. It shows that under the right conditions, nature builds a reactor that holds onto its waste for geological ages. The fission products barely moved. If the constants had drifted substantially, many of those products wouldn't line up with the retention we see. That stability hints at something else. The Earth's conditions and the constants that shape them were steady enough for this slow machine to run and then sit undisturbed for 2 billion years. Meanwhile, the skeptic's case stands. If you want to claim that quasar spectra see a spatial dipole in alpha at the parts per million level, you have to reconcile that with Oklo's time-average stability at parts per 10^8 on Earth's world line. It's not impossible. A dipole can be spatial, strong far away, weak here. A field can roll in the early universe, then freeze by the time Oklo runs. Or different constants can co-vary to keep sensitive nuclear resonances pinned even as alpha alone would push them. Gatekeepers lean on Oklo like a shield. Come back when your anomaly passes this rock. Screenshot this. You don't beat a 2 billion year reactor with a glitch. You beat it with a theory that survives it. If your model can't pass Oklo clocks in the sky at once, it's not a model, it's a story. What nobody knew when Oklo was first dissected is how central it would become to the culture of this debate. It's the anchor slide in talks, the quiet benchmark that forces theorists to fine-tune their knobs. And it's a reminder that our planet has been measuring for us the whole time, leaving clues in ore and clay while we learn to count them. Deep time narrows the window. Deep space still teases it. So we turn to the early universe's own photograph, the cosmic microwave background, to see what was imprinted when everything was hot, dense, and young. Cosmic microwave background and the early universe's signature. The baby picture with a secret. While deep time wrote clues into rock, the early universe wrote them into light. The cosmic microwave background is the baby picture. Photons launched when the universe cooled enough for protons and electrons to hold onto each other. That last scattering moment froze ripples into a modeled pattern across the sky. Hidden in those ripples is a ledger of the constants that set the rules back then. Here's the stake. Change the fine structure constant in that hot plasma and you move everything. How tightly atoms bind, how often photons scatter, the exact timing when the fog clears. Those details shape the angular power spectrum, the peaks and troughs that Planck and WMAP mapped with ridiculous precision. Shift alpha and the peaks shift with it. Screenshot this. The baby picture has metadata. Touch alpha, the CMB edits itself. Action first. Satellites spent years scanning the whole sky, stripping out foregrounds, calibrating detectors, and collapsing a billion temperature measurements into a spectrum. The first acoustic peak tells you the size of the sound horizon, how far pressure waves traveled before recombination. The second and third peaks tell you the ratio of baryons to photons, the amount of dark matter, the damping at small scales where diffusion erases contrast. All of this is sensitive to how easily electrons and protons meet and stay together, which depends on alpha. Make alpha larger and hydrogen binds more tightly. Recombination happens a bit earlier. Photons decouple sooner. The sound horizon is smaller. The peak positions slide. Planck teams fit models to this spectrum, not by eye, by exploring a high-dimensional parameter space. The standard set includes 6 core parameters. Add a knob for alpha, let it float, and ask the data how much wiggle room is left. The answer is, not much. If you keep the rest of the model intact, flat geometry, cold dark matter, a cosmological constant, the CMB locks alpha near the present value within a few parts per thousand at recombination, and fixes H0 near 67 km/s/MPC in that framework. That's a broad brush compared to the quasar ppm whispers, but it's at a time 380,000 years after the Big Bang, when the physics was very different. The early universe says, you can't move alpha far without messing up the peaks. But there's a catch, the degeneracies. Vary alpha and you don't just move one dial's output. You can partly compensate by adjusting the baryon density, the Hubble parameter, or the scalar spectral tilt. That's the model dependence trap. If alpha creeps, the fit can shove other parameters to soak up the change. The spectrum still looks good, but your measurement of alpha now depends on choices under the hood. Planck papers spell this out. Constraints tighten or loosen depending on what else you allow to float. Meanwhile, polarization adds a second witness. The E-mode polarization peaks arise from the same acoustic physics but respond differently to scattering. Fold in polarization, and the parameter covariances shrink. You get sharper bounds on recombination history, hence on alpha then. The fits still say small wiggle room, percent level at most, but the path there shows how interlocked the constants and cosmological parameters are. Here's where the human debate gets loud. One side, the CMB kills large variation, end of story. The other, careful. You've assumed a cosmological constant, fixed neutrino physics, and no exotic couplings. Relax those and alpha's leash lengthens. Papers trade scenarios. Allow early dark energy, allow extra relativistic species, allow a time-dependent dark energy equation of state. Each one stretches or tightens alpha's corridor. While that's happening, a deeper point bubbles up. The CMB is mostly sensitive to dimensionless combinations, ratios that don't care about units. That's a sanity check. Change a dimensionful constant like c by definition and you're just changing your ruler. What matters are the pure numbers. Alpha, the electron-to-proton mass ratio, the gravitational strength in Planck units. The CMB, like the quasar spectra, cares about those. Impact? Even with degeneracies, the early universe sets guardrails. No model where alpha wandered wildly through recombination survives without breaking the peak structure. That pushes theorists toward gentler evolution or spatial variations that average out over the last scattering surface. It also feeds back into the quasar dipole story. If a spatial gradient exists today, was it present at recombination? If yes, it would imprint a preferred direction in the CMB. Planck's sky does show mild hemispherical anomalies, but nothing cleanly aligned to an alpha gradient. That tension forces any dipole mechanism to be subtle. Maybe the field rolled after recombination, or the effect couples weakly to photons at early times. Complication keeps circling. Recombination physics itself is a careful enterprise. Multi-level hydrogen, helium, 2-photon decays, radiative transfer in the Lyman lines. Teams like Cosmo-Rec and High-Rec built detailed codes to get it right. A small misstep there can masquerade as a constraint on alpha. So the community did the boring, necessary work. Independent codes, cross-checks, validation against laboratory measurements of atomic rates. The conclusion stayed steady. Within these improved recombination models, there's limited room for alpha to move at Z110. Human beat. Picture the group huddled over a residual plot at 3 p.m. in a windowless Planck office, arguing over a 0.2% bump at multipole L120. The bump vanishes when they tweak a foreground model. Relief in the room, but also fatigue. They've been hunting ghosts for months because they know any whisper of drift could hide in the same bin as a dust template error. Meaning lands like this, the CMB doesn't settle the constant question, but it fences the playground. It says the early universe wasn't wildly different in the electromagnetic rules. That's not the same as saying the rules never drifted. It sets the stage for theories where constants are fields that barely moved at recombination and may have slid later or vary in space more than time. Thumbnail line. The baby universe says, not too much. Early guardrail set, now stress test the limits. If alpha is on the table, people ask the reckless question next. What about the speed limit itself? If C isn't fixed, causality and the whole cosmological story twist. That's where the mavericks walk in. Speed of light theories, VSL versus inflation. The speed limit might be a setting. If light was faster before, your map of causality is wrong. Here's the stake. If the speed of light isn't fixed, causality and every deep assumption in cosmology gets a stress test. The horizon problem, the question of how opposite ends of the sky look the same when light shouldn't have had time to even the temperature, suddenly has a different door. If C was larger in the early universe, information could have flown fast enough to iron out the wrinkles. No inflating space needed. That's why the idea keeps returning, even when the room gets chilly. Action starts at the end of the 20th century. A handful of theorists, tired of patching the standard model with just-so beginnings, wrote down varying speed of light theories. Moffat, Albrecht and Megiddo, Barrow, they sketched dynamics where C depends on a field that took different values in the early universe. In those models, C relaxes to today's value, leaving a uniform cosmos behind. The math wasn't a hand wave, it was a program. Modify the Einstein equations or the matter sector so that the causal structure changes at high energies, then recover the usual light speed later. Meanwhile, inflation was already winning. A brief, furious expansion early on solves the same horizon and flatness problems by stretching a tiny, uniform patch to cosmic size. Inflation predicts a near-scale invariant pattern of primordial fluctuations, something the CMB sees. It gives you a mechanism for seating structure. It even explains why space looks flat without needing a fine razor balance. VSL had to compete with that record. Here's where it gets interesting. VSL isn't one theory, it's a family. Some versions keep Lorentz invariance locally and let C vary cosmologically through a scalar field that changes the effective light cone for certain interactions. Others break Lorentz symmetry outright in the high-energy regime and glue it back at late times. Some fiddle with how units are defined. Others anchor everything in dimensionless ratios and embed C variation in something you can actually measure, like how alpha or the horizon scale behaves. Then the complication that kills many conversations: units. If you change a dimensionful constant by declaration, you might just be changing your ruler. Physicists guard against that by asking, what dimensionless observables move? The fine structure constant is dimensionless. The ratio of the sound horizon to the angular diameter distance is dimensionless. VSL devotees know this. The careful ones translate every claim into those ratios. The careless ones get eaten in seminars. Meanwhile, inflation isn't bulletproof. It solves problems, but it raises others. Which potential drives it? Why that slope? Why that initial condition? Some versions produce eternal inflation and a multiverse you can't easily test. Observationally, Planck boxed in many simple inflation models and saw no obvious primordial gravitational waves at the levels some hoped for. That opened a small window where alternatives like VSL could pitch. Maybe there's a different causal story with fewer untestable branches. Nobody in polite company says, "What if C moved?" But the math lets you ask it. Human beat, get this. One of the most vocal VSL advocates walked into a top-tier department and wrote C equals CT on a board. Someone snorted. He kept going, chalked dust on his sleeve, mapping how a time-dependent speed of light in the early universe could generate the right spectral tilt. 10 minutes in, the laughter stopped. Not because he won, but because the math closed and the predictions landed in ranges you could compare to data. Impact? Even if VSL never dethrones inflation, it forces clarity. It makes inflation defenders specify what's essential and what's convenience. It pushes everyone to tie claims to dimensionless signatures and to spell out which sectors like cone they mean. Photons, gravitons, both. It also connects to our earlier thread. If constants vary because of fields, those fields can couple to electromagnetism and gravity differently. A universe where alpha drifts and C shifts might be two facets of one rolling field. Observational tests bite back. The CMB's acoustic peaks anchor the sound horizon, which depends on C and the plasma's properties. Baryon acoustic oscillations in galaxy surveys measure the same scale frozen into matter. If C was wildly larger at recombination, you'd expect a mismatch unless other parameters compensate. Some VSL models build that compensation in. Others die on the spot. Polarization patterns, lensing of the CMB, Big Bang nucleosynthesis yields of light elements, all add constraints. And multi-messenger constraints bind late-time deviations. The neutron-star merger GW 170817 showed gravity and light speeds agree today to astonishing precision. You can't crank C without knocking these down like a row of dominoes. There's also the gravitational wave frontier. If gravitons felt a different effective speed in the early universe, primordial gravitational waves and their imprint in B modes would shift. LIGO's multi-messenger event from a neutron-star merger measured the difference between gravity and light speeds today to absurd precision. No room for late-time deviations. That pushes viable VSL into early epochs and into models where speeds converge quickly. Meanwhile, the unit choice trap keeps reappearing. A good sanity check. Phrase everything in Planck units where C, H-stroke, and G define the scale. If you let C vary there, you're really letting the mapping between those units and matter's couplings move. That circles you back to the dimensionless constants, alpha, the mass ratios, the gravitational strength compared to particle masses. The story keeps pointing to them as the honest currency. Human moment, a grad student skeptical of VSL tries to reproduce a key plot from a VSL paper late at night. The curve won't match. They email the author expecting a brush-off. Instead, they get a notebook and a candid note. Here's the catch. If you don't vary the electron mass with C, you'll break BBN. Try this coupling. The student runs it. The curve lands. Doubt remains, but respect grows. Meaning threads through the debate like this. VSL isn't heresy for sport. It's a pressure test on our comfort with fixed rules. Inflation earned its place by prediction and consistency. VSL earns attention when it ties itself to clear, testable, dimensionless consequences and survives the crossfire from CMB, BAO, BBN, and gravitational waves. Most versions won't. A few might. Hook. What if light was faster before? Screenshot this. If you vary units, you fool yourself. Vary a pure number, you change the world. And here's the pivot we need. Talking about C reminds us that the constants that really matter for change are the pure numbers. If anything's going to drift in a way we can trust, it'll be those dimensionless combinations that set chemistry, spectra, and stars. That's where the chase tightens next. Dimensionless truth, why only certain constants matter. Numbers you can't redefine. If it's not a pure ratio, it's a ruler trick. Here's the pivot we've been circling. Only certain constants are even allowed to change in a way that means anything. If you tell me the speed of light changed, but you also changed the length of your ruler and the tick of your clock, you didn't discover new physics, you rewrote your units. The honest currency is dimensionless. That's where reality hides the numbers you can't rescale away. Alpha is one of those numbers. So is mu, the proton-to-electron mass ratio. In gravity land, you can recast g into Planck units and ask about the strength of gravity relative to the rest of physics, another dimensionless measure. These ratios are the ones that sculpt chemistry, spectra, and stars. Move them and you move the world. Action starts by tightening the target list. Alpha sets the spacing of spectral lines and the chemistry playbook. Mu decides how heavy molecules vibrate and rotate, because the nuclei's inertia sets the beat. The gravitational coupling, written as g times the proton mass squared over h/c, tells you how strong gravity is compared to quantum forces. If you want to know whether the periodic table stays familiar or stars burn the same way, you track alpha, mu, and gravity's dimensionless strength. Now what happens if you nudge them? Let alpha slip by a few parts per million and atomic energy levels shift. Double bonds stretch or compress. Reaction rates change by measurable ticks. Colors of absorption lines drift. For mu, small changes move molecular lines more dramatically because vibrational and rotational energies scale with reduced mass. That's why cold clouds of molecules, ammonia, methanol, hydrogen, become microscopes for mu across the universe. Gravity's dimensionless strength threads through stellar structure. It sets how massive a star must be to ignite, how long it lives, how pressure balances against collapse. Push it and you redraw the Hertzsprung, Russell diagram. Observers went hunting with this in mind. Radio astronomers tuned to methanol and ammonia lines in distant galaxies. Those lines have different mu sensitivity coefficients. Compare them and you get a direct probe of mu at redshifts of half the universe's age. In some systems, the offsets land within a few parts per million of today's value. In others, the uncertainties are bigger, tangled with cloud dynamics and velocity structure. That's the complication. Molecules live in messy places. You need multiple transitions, multiple species, and clean kinematics to avoid fooling yourself with two clouds at slightly different speeds masquerading as a constant drift. Meanwhile, optical spectroscopists chased molecules in the ultraviolet, molecular hydrogen toward quasars. The lines are faint, the forests thick, but the payoff is high. H2 transitions carry different mu sensitivities, so a pattern across dozens can shout or silence a drift. Some analyses claimed hints at ppm level changes. Others, with improved calibration and more conservative line selection, flattened them to consistent with zero. The story rhymes with alpha S. Signals flirting with significance, systematics rushing the stage, teams arguing over which lines to trust. Back on Earth, precision labs joined the chase. Spectroscopy of simple molecules, HD+, H2+, trapped and laser-cool, ties mu to frequency standards. Pair that with optical clocks and you can measure drifts in alpha and mu simultaneously by comparing carefully chosen transitions. One more alpha-sensitive, one more mu-sensitive. That's not just clever, it's necessary. If both move, a single ratio can hide a conspiracy. 2 or 3 ratios break it, revealing which number slid. Human beat. A spectroscopist pulls up a fit to 80 molecular lines at Z2. The residuals look random, but a colleague points to a subtle trend with wavelength. That's a calibration comb's fingerprint sneaking in. They redo the reduction with a laser frequency comb reference. The trend dies. Their claimed non-zero mu drift drops by half, now within the error bars. It's a small heartbreak, but it's also the culture. If you can kill your signal with better calibration, you must. Off camera, someone says, don't tweet it. Impact radiates outward. The tighter the mu and alpha bounds get, the narrower the path for theories where a scalar field couples to electromagnetism and the strong force. A rolling field that nudges alpha will typically nudge quark masses too, and through them mu. Equivalence principle tests then feel it as an extra force depending on composition, a fifth force. Torsion balance experiments and lunar laser ranging hammer those couplings. If you want drift without a fifth force detection, you have to thread a needle, couple weakly to matter here, more strongly to photons far away, or let spatial variations live where our instruments are. Here's a subtlety people don't say out loud at first. The constants might co-vary to keep some observables nearly fixed. Screenshot this. 2 sliders can fake a straight line, drift together and the resonance looks stable until a different test yanks the mask off. That's not magic. It's a model where one field controls multiple couplings. You can hide a lot from Oklo and stars if knobs turn together, but the hiding isn't perfect. Different systems, atomic clocks, molecular clouds, stellar nucleosynthesis, pull on different combinations. Cross-compare enough of them and the conspiracy unravels. Smoking gun, cleaner than rhetoric. If you can measure it without changing your ruler, it's real. And if it's real, it can move. The gatekeepers know this. That's why they spent decades treating constants like sacred objects. Because once you admit only pure ratios matter, you admit those ratios can slide. Not by decree, by data. Meaning lands here. Chasing dimensionless constants keeps us honest. It strips away unit games and forces any claim to show up in ratios nature actually cares about. It also clarifies the stakes for life. Change alpha and mu beyond tight windows and chemistry becomes unrecognizable, stellar furnaces misfire, planet formation shifts. The universe looks tuned not just in one number, but in a web of them. From numbers to furnaces, if the knobs twitch, stars shout. And now that web feeds the next question. If tiny shifts in alpha and mu could tilt chemistry and fusion thresholds, what does that do inside the cores of stars, where small nudges meet huge consequences? Stellar hearts and nuclear thresholds on edge. The recipe for carbon has a hidden knob. Move one digit and a billion worlds go hungry. Inside a star, constants aren't abstractions, they're levers. A few parts per million in alpha or mu, and the nuclear thresholds that decide what a star makes, how long it lives, even if it ignites at all, start to slide. That's the stake. A whisper at the fundamental level magnifies into a shout in stellar cores. Action begins with a fragile miracle: carbon. Most carbon in the universe comes from the triple alpha process. Two helium nuclei collide to form a shaky beryllium-8, which usually falls apart in a blink. But if a third helium arrives fast enough, and if the combined system passes through a very specific excited state in carbon-12, the Hoyle resonance, the reaction sticks. That resonance sits at just the right energy to amplify the reaction rate by orders of magnitude. Move it a little, and the stellar recipe changes. Here, S where alpha enters. The position of the Hoyle resonance depends on the balance between the strong nuclear force pulling nucleons together and the electromagnetic repulsion between positively charged protons pushing them apart. Nudge alpha up and you strengthen the repulsion, sliding the resonance. Nudge it down and you ease it. The sensitivity isn't dramatic in everyday lab terms, but in fusion it's ruthless. A few tens of keV shift in the resonance energy can throttle carbon production or send it into overdrive, altering how much oxygen follows in the alpha capture chain. Modelers have mapped this terrain. Run stellar evolution codes with slightly different fundamental inputs, and you watch the carbon-oxygen ratio at the end of helium burning swing. Too much shift and you get stars that overcook carbon into oxygen and heavier elements, starving carbon-rich chemistry later. Too little and you pile up carbon, starving oxygen. The allowed window isn't razor-thin, but it's narrow enough that a drifting alpha is playing with the knobs of life's pantry. Meanwhile, gravity's dimensionless strength sets the stage for which stars exist to do this dance. Change it, and the minimum mass for hydrogen ignition moves, the pressure balance in cores rewrites, and lifetimes bend. Long-lived, steady-burning stars like the Sun rely on a precise tug-of-war between thermal pressure and gravity. If gravity relative to nuclear scales were stronger, stars would be smaller and faster burning. Weaker, and many wouldn't ignite or would linger too long, never forging enough heavy elements. Back in the core, other thresholds lurk. The proton-proton chain that powers small stars and the CNO cycle that takes over in heavier ones have rates that depend sensitively on tunneling probabilities and reaction Q values. Those depend on nuclear masses and electromagnetic barriers. Small shifts in alpha and in quark masses ripple into those rates. You don't need a big change to move a star's convective boundaries or to alter when shell burning ignites as it ages. Human beat. A theorist spends weeks nudging a resonance by 25 keV in a code, watching the output carbon-oxygen ratio tick from 0.3 to 0.7. Knuckles crack, a tired grin, because that's not just a number, it's the chemistry of future planets. In the next office, A nuclear physicist wrestles with lattice QCD outputs that tie quark masses to nuclear binding energies, arguing over uncertainties that look tiny on paper but stretch into a factor of 2 in a star's fate. Down the hall, someone stares at sensitivity curves, derivatives that say if alpha shifts by X, the reaction rate shifts by Y, and feels that steady, quiet pressure. Digits matter. Complication shows up with the anthropic whisper. If the Hoyle resonance is so finely placed, some say, of course it must be tuned or we wouldn't be here to ask. But the physics path doesn't end with a shrug. You can build models where a scalar field controls multiple couplings so that the strong and electromagnetic pieces co-vary, keeping the resonance near useful values even if individual constants slide. That buys you stability but not infinity. Push too far and the conspiracy fails. Different parts of nucleosynthesis feel different combinations, and the mismatch shows. Observational threads are starting to tug on this. White dwarfs, the carbon-oxygen embers of sun-like stars, carry a memory of the carbon-oxygen balance they were born with. Astrocosmology, reading their pulsation modes, can probe that balance. If constants drifted enough to tilt fusion thresholds over cosmic times, you might see trends in white dwarf interiors across populations. It's early, it's messy, but it's a path where stars themselves become detectors. Meanwhile, supernovae sit at the end of this chain as brutal auditors. Type Ia supernovae rely on carbon-oxygen white dwarfs reaching a critical mass and igniting runaway fusion. Change the carbon-oxygen ratio or the ignition conditions, and the light curves. Our distance ladders shift. If constants drifted enough to alter that ignition threshold over billions of years, the standardization we trust would wobble. That loops back to cosmology's tensions and keeps everyone honest. You can't change nucleosynthesis without risking your yardsticks. Here's a micro story. A code crashes at 3 a.m. because a resonance drift pushed a reaction rate out of a table's bounds. The grad student fixes it, reruns, and watches a population of stars live 1,000,000 years shorter. It's a footnote in a draft, but it's also a reminder. Thresholds in stars are cliffs, not ramps. The quiet horror is this. A ppm nudge here echoes as 1,000,000,000 fewer worlds there. Impact lands wide. Stellar lifetimes, element yields, the habitability clock of galaxies, all lean on thresholds touched by alpha, mu, and gravity's relative strength. If those numbers drift, even in parts per million, integrated over billions of years and through billions of stars, the universe's chemical story bends. The web of feedback tightens. Oklo constrains the past locally. Quasars tease spatial tilts. Clocks police the present. Stars magnify small differences into astrophysical consequences we can, in principle, read. Meaning then, the universe looks tuned not just because one number sits pretty, but because many sit in a coordinated range that lets fusion teeter at the right edges. The question isn't only whether it's tuned, it's whether it's tuned and stable, or tuned and drifting so slowly that the middle remains livable while the edges shift. That's the pivot to fields that can set and slowly move these numbers, and to the idea that laws might be the local weather of deeper dynamics. The multiverse, scalar fields, and slow drifting laws. The laws are local weather. When fields move, laws are just the forecast. If the constants feel like knobs, who's turning them? The simplest answer isn't a committee of gods, it's fields. In modern physics, fields set what particles weigh, how they charge, how they talk. Give one of those fields a slow roll across space and time, and the constants become snapshots of where that field happens to be. Laws turn into local weather, changing so slowly you mistake motion for calm. Action starts with scalar fields, the quietest kind. We already live with one, the Higgs, whose value decides the masses of fundamental particles. The trick is imagining cousins of the Higgs that don't sit perfectly still. Let a light scalar field couple to electromagnetism and its value sets alpha. Let it couple to quark masses and through them mu. If that field varies across the cosmos, you get a spatial gradient, a dipole like the quasar map hinted, without ripping the universe apart. If it rolls in time, you get tiny drifts that clocks might catch and Oklo constrains. The idea blooms into families. Quintessence fields, proposed to explain dark energy, are scalars that crawl down a shallow potential, changing the vacuum's pressure as they go. If the quintessence field talks to photons or to the QCD scale, it drags constants along. Chameleon fields hide in dense environments by becoming heavy there, dodging fifth force searches on Earth while staying light in intergalactic space where they can move constants. Dilatants from string theory show up as natural candidates, fields that want to rescale couplings and lengths, but can be tamed by mechanisms that suppress their effects locally. Meanwhile, the multiverse enters as the backdrop, not a punchline. In many inflation and string scenarios, different regions of the larger spacetime settle into different vacuum states, each with its own field values. That sets different constants in each patch. We see one slice, the bubble we grew up in, where alpha, mu, and gravity's relative strength land in a range that makes stars and chemistry workable. That's the anthropic whisper with teeth. Selection, not design. But even inside our patch, a field can still drift, slowly, leaving today's values slightly different from what they were a billion years ago across the sky. Complications hit fast. Couple a scalar to matter and you usually get equivalence principle violations, composition-dependent extra forces, torsion balance experiments, atom interferometers, lunar laser ranging, planetary ephemerides. They're all brutal enforcers, limiting how strongly such fields can pull. That's where chameleons and screening mechanisms came from. Make the field's effective mass depend on the local density so it hides in labs and planets, then lightens in voids. It's elegant but not free. The same trick that hides the force also slows the field's drift, shrinking the expected constant variations. Threading this needle means choosing couplings just so, enough to matter far away, small enough to evade every lab test here. Gatekeepers call this naturalness. To you it looks like moving targets. The point isn't a villain, it's a filter. Extraordinary claims must walk through narrower doors. Screenshot this. When the rules move, truth belongs to whoever measures faster and admits it first. Theory narrows, tests multiply. Now tie fields to fate. Human beat. A theorist sits in front of a whiteboard covered in potentials, flat plateaus, shallow wells, tiny ripples, asking which shapes produce a drift small enough for Oklo, big enough for quasars, and not killed by clocks. They erase, redraw, erase again. Across town, an experimentalist points at a torsion balance plot that drops any unscreened coupling below a line so low it feels like the floor. Between them, a student patches a code to evolve a scalar on a lumpy matter distribution, watching gradients form between clusters and voids. Impact shows up as possible unification. If a scalar drives dark energy and also nudges alpha, the quasar dipole and a changing cosmic acceleration could be two faces of one field. That's not just storytelling, it's predictive. If the field rolls, the dark energy equation of state parameter W deviates from and evolves. As it rolls, alpha shifts in sync. Measure one precisely and you can forecast the other's drift rate. That's a test. Monitor quasar absorbers across the dipole's axis while stage IV dark energy surveys pin WA. Do the two datasets dance together or not? Another thread, spatial variation. A scalar frozen by Hubble friction during recombination could start moving later as the universe thins out. That dodges CMB constraints but leaves structure era signatures. If the field gradients align with the large-scale structure, superclusters, voids, you'd expect subtle correlations between galaxy environments and any constant-sensitive spectral measurements. Radio campaigns are starting to target absorbers near different cosmic structures to look for this. Then there's the nuclear clock twist. Some nuclear transitions, like the thorium-229 isomer, are predicted to be hypersensitive to changes in both alpha and the strong force. A rolling scalar that couples to QCD would move that transition energy by many times more than an atomic line. Build two clocks, one atomic, one nuclear, and let them run. If the scalar exists, their ratio drifts with a slope set by the couplings. If it doesn't, the line stays flat, and another class of models narrows. What nobody knew a decade ago, and people quietly catalog now, is how many constraints you need to bind one field. You need quasar maps for space, clocks and Oklo for time, equivalence tests for couplings, CMB and BAO for early history, supernovae and lensing for dark energy behavior. Each constraint slices the parameter space like a plane through a 3D object. Enough planes and you either corner a viable shape or you cut it to dust. Human moment, an email thread with 17 names and 45 replies, arguing whether a new dipole fit should allow a correlated variation in mu tied to alpha by a gut-inspired ratio. Someone cites an old string compactification. Someone else points to a methanol absorber that hates that ratio. The final note is short. Run both fits. Let the data talk. Meaning stripped down. Scalar fields give you a straight path from whispers in spectra to the fate of the cosmos. If they exist and roll, the laws aren't laws, they're outcomes, slowly changing as the field relaxes. If they're caged or absent, the constants hold and the anomalies fade. Either way, the next step is obvious. If a field drives the vacuum's pressure, the universe's destiny depends on whether that pressure sits still or slides. Dark energy and the fate that won't sit still. Civilizations bet. If the backbone drifts, you either ride it or snap. If a scalar field can nudge alpha, it can also push on the vacuum itself. That's the stake. The pressure of empty space decides the universe's long game. For 25 years, we've called it dark energy and pretended it was simple, a cosmological constant with W equals -1, unchanging pressure that dilutes but never dies. But if that pressure evolves, the ending of everything tilts. Stars fade differently. Structures freeze or tear. Time's arrow gets a different slope. Action traces back to supernova light curves in the late 1990s. Distant Type Ia supernovae looked dimmer than a decelerating universe would allow. The expansion was speeding up. The simplest fix was a constant vacuum energy, Einstein's old lambda. That constant slides into the equations cleanly, no dynamics, no drama. It fit early data just fine. Then the precision wars began. More supernovae, better calibrations, baryon acoustic oscillations mapping a standard ruler in galaxy clustering, and the CMB pinning down the early geometry. Analysts fit everything together and asked, does the data demand W equals -1, or merely tolerate it? Meanwhile, theorists wrote down quintessence, a field rolling downhill in a shallow potential, its kinetic energy small, its pressure negative but not fixed. In those models, W floats above and changes with time. Others toyed with phantom energy, where W dips below -1 and the pressure is so negative it drags expansion faster and faster, ending in a big rip if it stays that way. The math is straightforward, the consequences aren't. If W isn't -1, every timeline you've seen in a cosmology poster is provisional. Recent DAISY analyses even hint, at roughly 4.2 sigma, at evolving dark energy when combining datasets, sharpening the stakes. If that holds as surveys mature, the constant in dark energy may be a story we told ourselves while the field kept moving. Complication rushes in from both sides of the telescope. Supernovae are standardizable, not standard. You correct their brightness with stretch and color, but dust and host galaxy environments creep in. Calibration ladders link nearby supernovae to far ones through Cepheids, tip of the red giant branch stars, and cross-instrument photometry. One misstep and W moves. On the large-scale structure side, bow measurements rely on understanding how galaxies trace mass, and weak lensing, measuring the subtle distortion of galaxy shapes by intervening mass, demands control of shape systematics and photometric redshifts. Every dataset carries gremlins. While that's happening, something else goes sideways. Tensions start to show. The Hubble constant inferred from the CMB, assuming a pure cosmological constant, lands at about 67. The local universe ladder says 73 or higher. That gap breeds ideas. Early dark energy, an extra push before recombination, eases the tension in some fits. Evolving W can also flex the distances slightly. DAISY, the latest big spectroscopic survey, maps bow at multiple redshifts and whispers that a constant W might not be the whole story, hinting at evolution at a few sigma. It's not a verdict. It's a nudge to reopen the case. Human beat. In a noisy conference hall, two teams huddle over the same triangle plot, contours of W and Y, the parameters that describe W, A equals W plus Y 1A. One group points to a mild preference for Y, implying W drifting toward -1 with time. The other points to a systematic in supernova calibration that, if fixed, shrinks the wiggle. Neither side claims victory. Both send students back to reprocess data. It's not cynicism, it's survival. Tiny shifts in priors and how you handle outliers swing the conclusion. Now fold in the scalar field story. If a field drives dark energy, it shouldn't sit completely still. Its motion would drag couplings a hair, linking W's evolution to potential drifts in alpha or mu. Clocks on Earth say those drifts are tiny today. Oklo agrees over geological time here. That pins the field to be either very weakly coupled to matter locally, screened in dense environments, or rolling so slowly that W hovers near -1 now. Far away, in thin cosmic voids, it could move more. That's a clean prediction path. If future supernovae bow and lensing tighten a case for evolving W, and quasar spectra find a coherent spatial pattern in alpha aligned with large-scale structure, the two stories start to rhyme. Impact shows up in the endings. If W is exactly -1, we get the big freeze. Expansion accelerates smoothly. Galaxies drift out of view, star formation dwindles, black holes evaporate over inconceivable eons, and what's left is thin and cold. If W and creeping upward, dark energy might fade. Gravity would reclaim dominance in the far future, slowing expansion, letting structures gently merge for longer, a slow thaw rather than a freeze. If W-1 and stays there, expansion runs away. Bound systems feel the tide. First clusters unbind, then galaxies, then solar systems, then matter itself as the scale factor's acceleration tears even atoms if the phantom persists. The timeline depends on how far below -1 you go and for how long, but the physics is merciless. Complication again. Current constraints allow only small departures from -1. That's the good news if you like continuity. It's the bad news if you're hunting a dramatic fate. The subtlety is that small departures now can integrate into big differences later. A W, that's -0.98 today, but climbing could hit -0.9 in a trillion years, enough to tilt the balance. The universe is patient. Small biases compound. Human moment. A grad student stares at a Fisher matrix forecast for a next-gen survey. The ellipse around W and Y shrinks with every added tracer. Emission-line galaxies, quasars, Lyman alpha forest. They do the math and realize a decade from now we'll measure W, tightly enough to call shots on most quintessence potentials taught in seminars. They print the plot and tape it to the wall, not as a flex, but as fuel. Meaning lands in one sentence. If dark energy evolves, fate isn't a constant, it's a story mid-chapter. And if that evolution ties to the same fields that tug on alpha, then the universe's end and the small anomalies in spectra are connected threads. That's not philosophy. That's a testable, fragile bridge. The next move's deeper supernova samples, ironed-out systematics in lensing, continental clock networks and quasar campaigns along suspicious axes, decide whether the bridge holds or falls. The Hubble tension and cracks in the cosmological model. Two rulers, one broken story. When two perfect rulers disagree, space or time is lying. While dark energy's story was getting complicated, a simpler number started a fight. How fast is the universe expanding right now? That's the stake. If the expansion rate, h, doesn't agree between the early universe and the late universe, something in our model is off. It's not a small squabble. It's a 5 sigma rift that won't close with polite emails. Action begins with two rulers. The first lives in the early universe, buried in the CMB. Planck measures the pattern, fits a model, and infers h by running the equations forward. You don't measure today's speed. You predict it, assuming the standard cosmology is right. The answer lands around 67 kilometers per second per megaparsec, km/s/mpc. Clean, precise, model time. The other ruler is local. Build a distance ladder. Measure Cepheid variables in nearby galaxies to calibrate type Ia supernovae, then use those supernovae to leap across the universe and read h directly from recession speeds versus distance. The SH0E's team and others do this with relentless care. Their answer sits around 7374 km/s/mpc. The error bars shrank, but the numbers didn't meet. The gap widened into a canyon. Complication arrives in waves. Critics of the latter point to Cepheid crowding, stars blending in Hubble Space Telescope images, biasing brightness. Others argue about dust metallicity, the way supernova-like curves get standardized. Latter defenders counter with crosschecks, replace Cepheids with tip-of-the-red giant branch stars, use maser distances where geometry rules, add detached eclipsing binaries, recalibrate with Gaia parallaxes. Each swap moves the number a whisper, not a leap. The local H stays high. Meanwhile, Planck skeptics ask whether the early inference leans too hard on a flawless model. What if the early universe had an extra dash of energy around recombination, early dark energy, that shrinks the sound horizon, changing the scale the CMB uses as its ruler? Do that, and Planck's model inferred H nudges upward, closer to the latter. But then bow measurements, frozen sound waves in the later universe, must also agree. Some early dark energy models thread that needle. Many get cut by bow and Big Bang nucleosynthesis constraints. The parameter space narrows, not vanishes. Human beat. A senior cosmologist famous for caution stands at a conference and says, "I don't think this is going away." The room shifts. For years, people blamed systematics. Now even the conservatives leave space for new physics. In a side room, a junior researcher presents a TRGB-based ladder that lands near SHES, different calibration, same high H. A murmur runs through the crowd. Different ladders, same summit. Other actors step onto the stage. Strongly lensed quasars with measured time delays give H without Cepheids or the CMB, mass models plus geometry. Their results lean high, with larger errors but independent lines. Megamasers in galaxy disks provide geometric distances. They agree with a higher H on the other side. Some galaxy clustering fits and cosmic chronometer methods lean low or split the difference. Everyone adds points. The tension holds. Impact cascades into theory. If constants drift or fields roll, they can tweak the expansion history. A field that changes alpha might also add early energy density or modify recombination, shifting the sound horizon and the CMB inference of H without wrecking the peaks. That's the temptation. One mechanism to connect spectral whispers and a cosmic rift. But the details are brutal. Change recombination, and you must keep the CMB's polarization and damping tail intact. Add energy early, and you must pass Bow's ruler test at lower redshift. Every creative fix hits a wall of crosschecks. Gatekeepers aren't wrong to demand this. They're just not eager to rebuild the model. Meanwhile, mundane systematics refuse to die. Planck's map-making choices, calibration transfer between instruments, foreground modeling, beam systematics, all were dissected. Successor analyses like ACT and SPT produce consistent early universe inferences within the lambdictum frame, keeping the low H anchor from that side. On the late universe side, new HSD and JWSD imaging sharpen crowded fields. New parallax releases clean 0 points. Still, the latter stands tall. Here's a micro story. A team celebrates a new JWSD observation of Cepheids in a far host galaxy, razor-sharp resolution, crowding crushed. They rerun the fit. H shifts by 0.3 km/s/MPC. The champagne goes flat. The tension is unchanged. Their paper's title softens, but the conclusion doesn't. Complication deepens with a thought. What if we're seeing patchiness? If a scalar field imprints a mild spatial gradient, could local measurements feel a slightly different expansion than the global early value? Large-scale structure makes our neighborhood underdense by a few percent. Could that bias H? Detailed simulations say local voids can shift H by maybe 1-2 km/s/MPC, not enough to bridge the full gap. The spatial dipole dream persists in hallway whispers, but rarely survives the slides. Human beat. Two camps share a table at a conference dinner. One pushes early dark energy, the other co-leads a ladder. They draw curves on napkins, sound horizons, distance moduli WA contours, arguing softly. The latter lead says, "If there's new physics, I want you to find it, but don't ask me to add noise until your model sticks." The early dark energy theorist nods, then says, "Then keep shrinking those bars. If you hold, we'll have to." Meaning breaks through. The Hubble tension isn't just a number fight. It's a credibility check on the entire cosmological model. If the early and late rulers won't reconcile under lambdictum, either hidden systematics remain or something about the model. Early energy neutrino physics, couplings that nudge constants, needs a patch. Conferences feel less standard with each data release. The cracks aren't collapse, they're stress lines. And when models wobble, gatekeepers tight. That clash, skepticism versus inertia, sets the stage for how the field polices ideas that threaten its constants. Screenshot this. Two perfect rulers disagree. Either space lied or time did. The pushback, peer review, reputation, and don't rock the constants. The gatekeepers. Standards save truth and strangle hype. While the Hubble fight spilled into plenaries, the pushback against drifting constants happened in quieter rooms, review panels, referee reports, hallway nods that mean, not yet. That's the stake. Careers, grants, and the unwritten rule that you don't swing at the pillars unless your data can't be ignored. Alpha, mu, W. Touch those and you're asking the community to risk its calibration of reality. Action starts with language. Early quasar papers that said evidence for spatial variation got rewritten, line by line, into possible hints under specific assumptions. Authors took out adjectives, added caveats, padded systematic sections until they doubled the results. It wasn't cynicism, it was survival. A strong claim invites a strong rejection, and rejections cost time and momentum. Teams learn to move by inches, to tie every step to a calibration, every calibration to a cross-check. Meanwhile, peer review sharpened its teeth. Referees demanded independent pipelines, blind analyses, and explicit tests where fake signals are injected and recovered. A quasar group would submit. The reply would come back with a list. Show a null test against solar lines in asteroid spectra. Demonstrate that wavelength distortions corrected by a laser comb flatten the residuals. Quantify the isotopic abundance degeneracy by marginalizing with priors from chemical evolution models. The authors would spend 6 months doing it, then resubmit. Sometimes the signal shrank, sometimes it held. Either way, the paper's tone cooled, the conclusion softened, and the door stayed barely ajar. Reputation threaded every decision. A young pie with a first big grant doesn't want a press cycle about changing laws blowing back when a calibration error surfaces. A senior figure with a prize on the shelf can spend capital on a risky interpretation. If it fails, they retreat with their CV intact. Quiet emails carry the subtext. Be careful, don't make us defend you in public if the next dataset flips the sign. Don't rock the constants isn't written anywhere. You feel it anyway. Nobody wants to be the name attached to laws are changing if it turns out to be a lamp error. The resistance isn't censorship. It's trauma from past false alarms. Then there are the retractions and walkbacks. A lab reports an annual modulation in clock ratios, tiny, maybe a coupling to solar potential. Months later, after a thermal control upgrade, the modulation fades. They publish an update that kills their own hint. A quasar team sees a dipole. A rival shows long-range distortions in the spectrograph that, if uncorrected, mimic the same pattern. The first group re-reduces with a comb anchor and reports a lower amplitude. The title changes from evidence to limits. The credibility, paradoxically, rises. Killing your favorite signal buys trust you can't get with rhetoric. Human moments stack up. A PhD candidate has a thesis chapter that lives or dies on a non-zero drift. Their committee urges caution. Write the null-friendly version, focus on methods. The student does it, gets the degree, and later publishes a careful null. Another researcher receives reviews that feel personal. The authors seem intent on resurrecting a dead idea and vents to friends. Then a third referee, anonymous and surgical, lists exactly how to salvage the analysis with a stricter line selection cut. The authors follow it. The claimed signal drops below 2 sigma, painful but honest. Complication is institutional. Big collaborations protect consensus. Planck, Dacey, SHES. Internal reviews are more brutal than journals. Drafts circulate, dozens of eyes search for overreach. Every superlative gets stripped. That's how those projects stay credible. It also means disruptive interpretations struggle to get past internal boards unless the case is overwhelming. Smaller teams outside the tent take more interpretive risks and get painted as mavericks. Sometimes they're right. Often they're early. Gatekeeping has a positive face. Standards rise. Laser frequency combs become expected. Absolute calibration to solar twins and asteroid spectra becomes routine. Blind analyses, where the key amplitude is hidden until all choices are frozen. Enter quasar and clockwork, borrowed from Cosmology. Pre-registered analysis plans show up in grant proposals. Metrology groups share environmental logs in real time to catch HVAC ghosts. Data releases include raw frames and reduction notebooks. forcing reproducibility. The bar to claim drift now requires multi-instrument agreement, cross-species ratios, and time baselines long enough to beat 1F noise. The villain here isn't a person. It's institutional inertia that only moves when the data won't let it stay put. But there's a shadow side. Null results can overshadow subtle anomalies. Journals love clean constraints with tidy figures of merit. Papers that map out messy systematics with no headline number struggle for attention, even when they do more for truth than 102.1 sigma plots. Funding panels ask for transformative potential and broader impacts, then dock points for risk. The safest path is to propose better clocks, better pipelines, better surveys, without promising to test an uncomfortable idea. The result is progress, but drift claims linger in the margins, never quite disproved, never quite embraced. Emails tell another story. A referee's private line. Your figure 4 is the only one that matters. Lead with it. A program officer's advice. Frame this as metrology advancement. Don't anchor the abstract on variable constants. A collaborator's memo after a rejection. We got bounced for tone, not method. Let's rewrite and remove claims. Keep the figure. That's the craft. Deliver the tools. Let the implications leak through. Impact lands in culture. The field now expects any extraordinary claim to arrive pre-defended. Multiple instruments, comb-calibrated, blind, with environmental logs, nulls, and cross-checks posted. That culture slows hype and accelerates reliability. It also means genuine anomalies take years to earn the right to be called anomalies. The upside: when a signal survives, it's already armored. Here's the tell that the ground is shifting. Workshops once titled Systematics in Precision Spectroscopy now include panels on physics beyond constants. Clock networks pitch their proposals as geodesy plus fundamental tests. Daisy and Euclid talks keep a slide for W, that isn't -1. You can feel the room allowing the question again, if not the answer. Don't rock the constants becomes, rock them carefully. Meanwhile, beneath the politics sits the question that cuts past reputation. What does any of this do to how we live? If the rules really shift, even a little, how does a civilization built on synchronization and prediction keep its footing? That's where the story heads next. If constants drift, clocks, chemistry, and civilizations bet. Your life runs on assumptions. Your GPS trusts a truce between atoms. We built a civilization on the assumption that nature keeps perfect time. That's the stake now. If the constants drift, we're balancing on moving ice. GPS triangulates your position by comparing nanoseconds across satellites. Financial markets timestamp trades to microseconds to settle disputes. Power grids phase match alternating current across continents. All of it works because a second in Tokyo equals a second in Toronto to absurd precision. If alpha or mu slide, even a little, the instruments won't agree unless we keep up. Action starts with the quiet revolution metrology already pulled off. In 2019, the SI units were redefined in terms of fixed constants, locking the kilogram to Planck's constant, the ampere to the electron charge, the Kelvin to Boltzmann's constant, and the second to the cesium transition for now. It was a bet that these constants are stable enough to be bedrock, but the redefinition came with a roadmap. Optical clocks, strontium, ytterbium, aluminum, already outperform cesium. The second will move to optical standards. That's not just better timekeeping, it's a new nervous system for the planet. Meanwhile, networks are forming. National labs link optical clocks with stabilized fiber that stretches hundreds of kilometers. Satellites will bridge oceans with optical time transfer that rides laser links instead of old microwave paths. QSNET in the UK, European and Japanese consortia, NIST and JILA in the US. They're stitching a fabric of clocks with different sensitivities to alpha and mu. Compare unlike clocks long enough and you don't just keep time, you test reality. If a scalar field whispers through, one ratio tilts, another stays flat. The pattern is the signature. Complication is mundane and relentless. Fiber links feel temperature gradients and strain. Ground terminals breathe with the weather. Satellites flex and atmospheric turbulence jitters phase. The engineers counter with two-way transfer, active delay compensation, adaptive optics on free space links, and redundancy. They log everything: rack temperatures, seismic noise, air pressure, because a half-degree hiccup can masquerade as drift. The discipline mirrors the quasar wars, but with spools of fiber and rooftop telescopes instead of spectrographs. Now zoom in on chemistry. If alpha walks, molecular energies shift. That flows into spectroscopy used in environmental monitoring, industrial control, and medical imaging. Gas sensors tuned to specific absorption lines could report the wrong concentration if the line moved enough over decades. It's tiny, but at scale, tiny matters. Pharmaceuticals rely on reaction kinetics calibrated to lab data. Process windows could creep. Semiconductor fabrication counts on lithography systems with phase-stable lasers. ppm drifts in refractive indices or photoresist behavior over many years would force quiet recalibrations. Power and navigation feel it too. Grid synchronization uses phasor measurement units tied to GPS time. If timing standards diverge subtly between regions, fault detection and islanding logic could misfire in edge cases. GPS relies on general relativity corrections baked into satellite clocks. If constants that set clock frequencies shift, those corrections must update. The good news is the system was built to absorb updates. The bad news is that updates assume the rules of today hold tomorrow. Human beat. An engineer in a grid control room watches oscillations ripple across a network after a storm. The PMU trace is just barely out of tolerance in one substation. They dig in and find a firmware update lagging, a clock offset by microseconds. It's a hiccup, not a catastrophe, but it's a parable. Coordination fails first at the margins. Now imagine a future where a slow, global bias creeps into time bases unless we correct for it. The fix isn't panic, it's infrastructure. Impact lands as two broad choices. 1. Detect and correct. We accept that if constants drift, we'll see it in cross-checked clock ratios and recalibrate everything that references them. GPS ephemerides, trading timestamps, telecom frames on a defined schedule. We do this already for leap seconds and relativistic corrections. We'd add constant drift tables to the pipeline. 2. Build an early warning system. A continental mesh of optical and nuclear clocks plus frequency-stable links acts like a physics seismometer. If a field is moving, spatial gradients show up as geographic patterns. You don't wait for markets to complain, you push patches proactively. Call it reality ops. There's also a civilizational upside. Chronometric geodesy, using clocks to read gravity, promises practical wins. Monitoring groundwater depletion, volcanic inflation, and sea level shifts by measuring tiny potential changes. The same sensitivity that would catch drift gives you a new environmental instrument. Timekeeping becomes environmental sensing plus fundamental physics, one network serving three masters. Complication returns with a philosophical edge. If we redefine the second on optical transitions that are more sensitive to alpha, are we baking in more exposure to drift? Maybe. But we can define the second by a convention and realize it with an ensemble of clocks, multiple species, including a thorium nuclear clock when it arrives. The ensemble's internal checks catch any one species wandering. That's how you hedge, by diversity. Human moment, a standards committee meets. The oldest voice in the room points out that locking units to constants was meant to end the era of artifacts drifting in vaults. A younger metrologist replies, "We didn't end drift, we moved it into equations we can monitor." The room laughs, not because it's a joke, but because it's the plan. Meaning stripped down is practical. A changing rulebook doesn't end predictability, it changes what prediction means. We stop pretending permanence and start instrumenting the drift. If the universe's parameters move, we trace their motion and fold it into the way we keep time, fly planes, settle trades, and balance grids. That's not surrender, it's adaptation. And by building the instruments that would save our systems, we also build the ones that decide the bigger question. Are the laws steady, Or are we living through a very slow change? Screenshot this. Measure like the rules are alive. Meaning under moving laws, free will, prediction, and trust. Can you trust tomorrow? Bet on motion, hedge with measurement. We've built our lives on the idea that nature keeps its promises. That's the stake if constants drift. How much of what we call choice, planning, and trust relies on the ground staying put? If the rulebook slides 1 millimeter a century, you won't feel it in a handshake. You will feel it in the long bets, climate models, infrastructure lifetimes, interplanetary missions, even the meaning of same across generations. Action starts with prediction. Science isn't prophecy, it's disciplined betting. You set priors, you update with data, you test the bet by seeing if it pays out. When the rules themselves can move, the bet changes form. We stop asking what's the number and start asking how is the number moving. That's a different psychology. It replaces certainty posters with velocity plots and error cones that widen with time unless you keep measuring. It's humbling, but it's workable. Meanwhile, free will sneaks into the room. If constants slowly evolve because a field rolls, is that determinism with longer gears? It doesn't change the fact that the future flows from the present. It does shift where agency lives. You can't choose alpha. You can choose to wire the world with instruments that notice when alpha twitches and to design systems that adapt. In practice, that's where freedom hides, not in freezing laws, but in building feedback that keeps your plans live as the backdrop drifts. Trust, the quiet currency of civilization, gets renegotiated. We trust clocks because they agree. We trust markets because timestamps settle disputes. We trust medicine because dose-response curves stay inside tolerances. If the background moves, trust doesn't vanish, it updates. We trust institutions that measure continuously and publish the drift. We trust devices that self-calibrate against networks. We trust models that admit their priors and posteriors are time-stamped, not timeless. Complication is human. We're bad at living with provisional truths. We crave closure. The constant is constant, the map is final. But the 20th century already trained us to live with uncertainty, quantum spreads, chaos, nonlinearity. This is the next step, uncertainty about the stage's parameters, managed with Bayesian humility. The move is simple to say, hard to practice. Assign priors to possible drifts, update them as clocks and telescopes report, let the posterior steer engineering margins and policy windows. You don't believe in drift, you price it. Here's a micro story. A mission planner for a deep space probe reviews a trajectory that threads a gravitational assist 20 years out. The team adds a line item, constant drift sensitivity. They run a Monte Carlo with tiny slopes in alpha and mu within current bounds, not because they expect trouble, but because the cost of being wrong is missing a slingshot you can't redo. The burn margin grows by a whisper. A decade later, a clock network report nudges the prior. The plan adjusts. No drama, just grown-up prediction. Meaning reaches down to identity. If the laws can drift, do they still count as laws? The answer lands in a sentence physicists don't say enough. Laws are patterns we compress the world into. If the pattern includes a derivative, this number is changing at this rate. It's still a law, just a dynamic one. The word constant becomes a special case, not the definition of physics. That's not a demotion. It's a better match to a universe that may be slowly relaxing rather than frozen. Thumbnail line: the rules are alive. There's also a moral angle. A civilization that knows its rulebook might be moving has a duty to instrument itself. That's not just to guard markets and grids. It's to keep the scientific record honest. If you want your grandchild to compare a spectrum you took today with one taken in 50 years, you owe them calibration that survives the drift. That means open data, archived pipelines, clocks that leave logs with their ticks. Continuity becomes an ethical choice. Human beat: a young researcher presents a result with error bars that include a small term labeled constant drift prior. An older colleague frowns. Isn't that overcomplicating? And the room waits. The presenter shrugs and says, it costs nothing to include what we already know we don't know. The tension breaks. The term stays. Culture shifts by inches like that. Impact comes back to trust. Institutions earn it by showing the scaffolding, assumptions, priors, updates, and by wiring policy to measurements in real time. Weather forecasts got better when we fed them more data more often. Rule forecasting will do the same. If a slow drift exists, it'll show up first as a bias in residuals across many instruments. If it doesn't, those residuals will flatline and confidence hardens. Both outcomes strengthen the bond between public promises and the physics beneath them. Meaning final pass. Moving laws don't erase meaning, they move it. Prediction shifts from declaring a fixed future to steering through a changing one. Free will shifts from picking outcomes to choosing sensors and feedbacks that keep outcomes within bounds. Trust shifts from assuming sameness to verifying it and correcting when it is. And the choice that matters most might be the simplest. Keep measuring anyway. Endgames from quiet freeze to violent rip. Choose your apocalypse. We've circled the possibility that the rules can move. Now we have to ask the blunt question, if they move even a little, where does that take us? That's the stake. Tiny drifts today can steer the universe toward endings that don't look the same. Some futures are quiet, some are not. Action starts with the baseline, the big freeze. If dark energy is a true constant with W equals -1 and the dimensionless coupling sits still, acceleration keeps stretching space at a steady, relentless pace. Galaxies drift beyond each other's horizons. Star formation dwindles as gas gets used up or locked away. Degenerate remnants, white dwarfs, neutron stars, black holes, dominate the landscape. Over unfathomable times, black holes evaporate by Hawking radiation. The night gets darker, colder, thinner. Chemistry ends not with a bang, but with no fuel left to burn. The freeze is a long farewell. But if the field behind dark energy rolls, the ending shifts. Picture a slow thaw. In quintessence models where W-1 and creeps toward over cosmic time, the acceleration eases. The universe still expands, but the push of vacuum pressure fades. Gravity gets a little more time to work. Structures keep merging, star formation smolders longer in fresh gas stirred by late infall. The end is still quiet, but the timeline stretches and the gradient softens. Galaxies don't race away as quickly. The sky's dimming takes its time. Then there's the cliff on the other side, phantom energy. If W dips below -1 and stays there, the scale factor's acceleration accelerates. Distances grow so fast that even bound systems can't hang on indefinitely. First, superclusters unbind. Later, galaxies shear apart. Push far enough and the tidal pull of expansion overwhelms the binding of solar systems. And in the most extreme models, even atomic bonds if the phantom persists. That's the big rip. The schedule depends on how far below -1 you go and how long you keep it there. A hair below -1 gives you trillions of years before the tide wins. A deeper dip shortens the runway. It's a violent future written by a small tilt in a single parameter. Now fold in drifting constants and the endings branch again. If a scalar field tugs alpha and mu while it drives W, the path to any end state picks up side effects. In a slow thaw, alpha might slide by parts per million per Hubble time. That's invisible to your eyes, but not to physics. Molecular energies shift. Fusion thresholds creep. The balance between carbon and oxygen yields from stars tilts a little as eons pass. Over billions of years, that bias compiles into different chemical landscapes in young galaxies. The late universe's material culture, planet composition, coolant lines in collapsing clouds, nudges off the track we'd predict under fixed constants. Quiet fate with a different flavor. In phantom futures, the drift can aggravate the tear. If alpha grows, electromagnetic repulsion strengthens, making atomic and molecular bonds a little more fragile just as expansion's tide rises. That doesn't decide whether atoms rip, it's the expansion that sets that. But it changes the threshold for when smaller bound systems start to feel strain. If mu shifts, molecular binding energies track it, moving the breakpoints again. These are second-order effects stacked on a first-order catastrophe, but they're part of the ledger. When everything stretches, The strength of what holds things together matters. Complication shows up as hope. Slow drifts might steer you away from the sharpest edge. A rolling field can approach a de Sitter-like plateau where W asymptotes to -1 from above. In those models, any changes in alpha or mu decay with time as the field slows. The far future looks almost constant again, a gentle freeze with the added footnote that the rules settled into place rather than being etched there from the start. If you want a universe that ages without breaking, that's the temperate zone. Human beat. A theorist sketches 3 curves on a board W, A that stays at -1, one that climbs from -0.98 to -0.9 across trillions of years, and one that dips to -1.05 and holds. Below, they draw 3 little panels, a star formation history that fades fast, one that fades slow, and one that plummets after a while when structures come unglued. In the corner, they scrawl d-alpha/dt, tiny slopes near 0 for the constant case, a soft bell for the slow thaw, a weird, sensitive wiggle for the rip as the field speeds up. It looks like too much meaning for such thin lines. It's not. Those lines pick who gets to exist late. Meanwhile, we check the other knobs. Gravity's relative strength enters the endgame through compact objects. If the field covaries coupling so that gravity's dimensionless strength drifts relative to particle masses, thresholds for collapse shift. The Chandrasekhar mass, the cap for white dwarfs before they give in, depends on those ratios. Tiny drifts tilt when stars end as white dwarfs versus neutron stars, altering the late-time inventory of remnants. Over immense spans, those inventory changes feed back into how often black holes merge and how mass gets locked away versus radiated. Observables might keep us honest even here. If alpha drifts with the field, then relics of an earlier drift could be encoded in the elemental ratios of very old stars, or in the statistics of white dwarf asterosismology across populations formed at different cosmic epochs. Clocks, if any civilizations last long enough to keep them, could directly track drifts on local timescales and report a slope. In a rip-leaning universe, that slope might steepen subtly as the field's kinetic energy grows. That's not folklore. It's a forecast you can make from specific potentials. Then there's a strange mercy that hides in the math. Even in a big rip, the approach is slow until it is. You get vast stretches where life, if it adapts, can build around the changing tide. The last acts are short compared to the eons before. In a long freeze, the opposite holds. Nothing dramatic happens, and meaning, if it exists, has to find itself in a thinning world where free energy becomes rare and community depends on long, slow bets. Either ending is harsh in its own way. The drifts, if real, don't choose the script, they edit it. Human moment. A late-night argument over coffee ends with someone saying, "We keep writing endings like we'll be around to see them." The room goes quiet. Then someone else says, "We won't, but we can write the instruments that would tell whoever is what the ending is." That's not defeatist. It's responsibility. Impact lands as a choice of posture. If the universe is headed for a freeze, drift, or not, then patience is the virtue and measurement is the craft. You ride the long slope and keep calibrating. If it's a thaw, you look for ways gravity can keep stirring the pot and for signs that fields are slowing. If it's a rip, you model how far below -1 you can be and for how long before bound structures feel it. And you look for signatures now, tiny deviations in W, A, coherent drifts in constants, that would tell you the script early enough to matter. The stakes aren't personal. They're about what kind of story physics tells when the rules are written by fields that move. Meaning last term, we don't get to pick the end. We do get to decide whether we face it with a clean record. Drifts are an invitation to watch the universe not as a finished thing but as something still settling. That's a better story than a static stage. It gives work to do. It makes the question worth asking. If the sea is moving, how fast is the tide and where is it going? Cliffhanger, 3 things will decide the verdict: quasar maps, a continental clock mesh, and a nuclear clock that feels the strong force. If 2 agree, the third can't hide. When the ratios tilt in sync, the laws won't be theories. They'll be motion. Be where the first slope breaks cover. This isn't trivia, it's civilization's bet. The experiments are running. Clock networks are listening. Quasar light is still arriving. And when the data lands, when we finally have proof that the laws themselves are shifting, the world changes. Models snap. Maps redraw. The rules won't be theories. They'll be motion. Be where the first slope breaks cover.